this video, I'm going to demonstrate how this very simple variable pitch oscillator is controlled via a number of buttons assigned to trigger different pitches. To increase the complexity of our circuit, we can create a series of different values for this resistance RT that feeds into this rightmost op-amp. In order to do this, we create a number of parallel paths with different resistance values in each. These, of course, are the potentiometers, but they are fixed at certain specified values, so I'm treating them as static resistors here in this diagram. These are normally opened buttons, and that means that by default they are not closed, so there is no sound coming out of the circuit, as we can hear now. This is fed in for our R total, and it goes in here, and it goes into this rightmost op-amp, as we could see before. That will go in right here. The primary equation I used to solve this stated that the output frequency was 1/4 times this RT value times the capacitance times the relationship between R2 and R1. R2 is this resistor right here, and R1 is this resistor right here. It was noted in the lab specifications that R2 has to be greater than R1 in order for the feedback and thus the oscillation to work correctly. Manipulating this equation in symbolic form allowed me to figure out what potentiometer values I would need for each specific frequency. In this case, the formula worked out as follows. The resistance of the potentiometer for each respective stage or button equaled 1/4 times the desired frequency out times our capacitance, which was fixed at 1 microfarad, times the relationship or ratio of R2 over R1, which was also fixed, minus the 1 kilo ohm resistor, which was in series with our potentiometers so that we did not have a value of 0 ohms feeding into the rightmost operational amplifier. Simplifying this equation further, we find that we can divide 2.5 times 10 to the negative 6 by our desired frequency and subtract our 1 kilo ohm resistance, which is fixed for RT. When designing this circuit, I decided to explore different perfect consonances. I decided that my lowest or supposed root note would be at 250 hertz. I then decided that I would make a second frequency, which was 1.5 that of our fundamental frequency of 250 hertz. This ended up being 375 hertz. The numbers after F1, so F2 through F4 and beyond, do not correspond here with the values I ended up choosing. That's because I made F2 1.5 times the original or fundamental frequency. F3 was twice the fundamental frequency, so 500 hertz. F4 was 3 times the fundamental frequency, so that was 750 hertz. And then a fifth value of F5 would be 1000 hertz, which is 4 times, or thus 2 octaves, above our fundamental frequency. Therefore, I expected to hear a number of B natural pitches with their perfect fifths in between. Those would be equivalent to F sharps or G naturals. Now that I had settled on the desired pitches for each respective key, I substituted these values into the equation I came up with before. So the first value for the fundamental frequency of 250 hertz is 9400 ohms, roughly. Actually, in this case, it worked out to be exactly 9400 ohms. For the second one, which would be 3/2 times the fundamental, or 1.5 times the fundamental, or 375 hertz, I ended up needing a value for my potentiometer of approximately 5670 ohms. It should not matter all that much at first. The potentiometer value for the third frequency of 500 hertz, or 1 octave above the fundamental frequency, was 4,000 ohms. The potentiometer value for the fourth frequency of 3 times the original frequency, or 750 hertz, ended up being roughly 2,330 ohms. And the final potentiometer value, F5, for 1,000 hertz, or 2 octaves above the fundamental frequency, that's 4 times the fundamental frequency, ended up necessitating a potentiometer value of 1,500 ohms. We have 6 potentiometers. One of them is controlling the output volume here, so we're not really going to consider it. For each of the values that I had determined on paper, I then used a multimeter to fine-tune, so to speak, the resistance values of each of these potentiometers so that they were as close as possible to the values that I came up with theoretically. Of course, I did expect some variation in the pitches and some inconsistencies, and as we will see in a moment, this is a valid concern. Now let us try our circuit. On the bottom, we have our lowest frequency, which is supposed to be 250 hertz. Right now it's being outputted as a square wave, but we could also output it as a triangle wave. Before the video, I'm going to leave it in the square wave mode. You will notice that as I move the capacitor around within the circuitry of the integrator, that is the rightmost operational amplifier subsection, the frequency will change dramatically. I will be careful from now on to not touch this capacitor so as to not inadvertently alter these outputted frequencies. According to my current design, every other output should be an octave above the previous one, starting with the lowest fundamental note of about 250 hertz. We have a rough sense of octaves now, but it is not perfect, of course. That is because these potentiometers are designed to change, and subtle movements to different parts of the circuit could easily alter the results. Buttons 2 and 4 represent perfect fifths above their respective octaves or roots on B naturals. Therefore, they would be F sharps or G flats. And as with the relationship between every other button, these two buttons are about an octave apart in pitch. As demonstrated here, the use of multiple buttons and different precisely controlled resistance values allows for the creation of synthesized tones via a simple operator amplifier circuit. Now let us take some time to adjust the potentiometers by ear and try to create as perfect relationships as we possibly can. These will most likely deviate from the values we determined originally via the multimeter, but that is okay because in the end what matters is how it sounds, not the numbers and the theories. I have taken around 5 to 10 minutes to tune it as best as I can to relative octaves and perfect fifths in relation to one another. You'll notice that I cannot play two notes at once that retain the same pitches. This is because this is a monophonic synthesizer of sorts, and the resistances, when two or more buttons are depressed, are somehow interacting with one another, which creates a different voltage as seen by the other operating amplifier. Now I return to the oscilloscope and I will play these notes and describe what I'm doing, and we will see their respective square wave outputs over here. So let's start with the fundamental note of roughly 250 Hertz. So we can see this is what comes up on the screen. And notice how long each period or cycle is. Now, if we go an octave up, we should see twice that frequency. So to compare it with the original, that's the original, and that's twice. You will notice that in half of one of these periods of the fundamental, we can fit a full cycle or full period of the octave higher frequency. And we can go an octave higher than that right here, and this is the result we get. Comparing it to an octave below, which is this, we get this. You can see again that twice as many cycles can fit into the same window of time. Now let us consider the perfect fifths. You will notice that when I compare the two perfect fifths relative to our root or fundamental, these with respect to one another will be an octave apart, and therefore we should see just about, or ideally exactly, twice the number of cycles in the wave outputted from this button compared to this button. Let us first press this button down here. This is the result we get. Notice how long the period is. Now let us press this button right here, and we should see something that has twice the frequency, and indeed we do, so therefore it is an octave higher. So the former, the latter. Now comparing the fundamental frequency to its perfect fifth, we have this result. Here's the fundamental, here's the perfect fifth. If I alternate quickly between them, it's rather difficult to tell the variation, but it's obviously not as big a difference as between an octave above and the fundamental. So here's between the fundamental and the perfect pitch, and here's between the fundamental and the octave. Now if we go between the fundamental and the perfect fifth plus an octave, which is the fourth button, or the second to last one from the top, there is an even greater change. If we then go all the way between this button and the topmost, we should see a fourfold increase in the number of periods per time division. That also means that the output of this button is 2 octaves higher than our fundamental. So let's press the fundamental first, and now let's press the button for 2 octaves higher. And you can see without question there is an enormous change. So here's the fundamental, here's the 2 octaves higher. This has been a demonstration of each of the individual tones in square wave format. Of course, the same happens if we shift from square wave to triangle wave. Now we see the fundamental, an octave higher, so there's the comparison, and between 1 octave higher and 2 octaves higher, and between the fundamental and 2 octaves higher. We also have our perfect fifths, which are an octave apart from one another. We will notice that the difference between the fundamental pitch and the bottom perfect fifth is not as great as between that and the first octave. So here is a comparison of the bottom fundamental frequency with the first perfect fifth, and now with the first octave. If we go one higher, comparing the fundamental to an octave and a perfect fifth above, this is the comparison we get. And if we go 2 full octaves higher than the fundamental, we see a fourfold increase in the number of periods we can fit into the same span of time. So that is a demonstration of the basic functionality of this circuit in relation to its individual production of different tones related to the amount of current going through each of them, controlling the feedback circuit in the operational amplifier. Also of interest may be the combination of different tones we can get by pressing multiple buttons at once. Now, because this is a monophonic synthesizer of sorts, that means that the individual notes will not be preserved. Instead, we will get a mixture of control voltages, which means that the sounds we would hear individually are no longer present, but we hear other tones. And if we look here, if I press the bottom two, we can see this is the result. The top is this, the bottom is this. Together we get an even higher wave. We can press other buttons in different combinations, sometimes 2, sometimes 3, and it seems that the more buttons I press, the more current is allowed to flow, so the resultant pitch as the consequence of the feedback gets higher and higher. So right now it's at its highest possible frequency for the configuration of resistances I have applied to each of the buttons. Thank you for watching this video. I hope that you enjoyed it and learned something, and I hope that you look forward to future videos that I will be posting about other electronics projects and principles.